Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over some example problems of how to relate the electrochemical potential of the cell to the equilibrium constant K. And so once again what we're going to need to do is we're going to have to break down our redox reactions into the two half reactions, oxidation and reduction. And we're going to have to use the electrode potentials to figure out what the electrochemical potential of the cell is. We're going to use this equation up here. The electrode potential of the cell is equal to, or the standard electrochemical potential of the cell is equal to the standard electrode potential of the cathode minus that of the anode. Once we get the standard electrochemical potential of the cell, we can now then use that in this equation here, where the standard electrochemical potential of the cell is equal to 0.0592 volts over the number of moles of electrons being transferred, multiplied by the log of K, and then you can solve for K. So let's get started with our first problem. So here we have copper solid being reacting with H plus to give you copper 2 plus and H gas. So here we have electrons that are going to be converted or transferred from the copper to the H plus, and so copper here is going to be oxidized. So we need to split these up. So we'll do copper. So copper solid is going to lose 2 electrons, so that's going to go to Cu2 plus aqueous plus 2 electrons. And then we have our hydrogen, that's going to be 2H plus aqueous plus 2 electrons. And that's going to go to H2 gas. Okay, so here we have loss of electrons. This is oxidation. Oil rig. Oxidation is loss of electrons, oil, and reduction is gain of electrons, oil rig. So we're gaining electrons, so that's reduction. This is reduction. And so again, oxidation is happening at the anode. Reduction is happening at the cathode. So if we use our equation here, the electrochemical potential of the cell equals the standard electrode potential of the cathode minus that of the anode. Now we just look up these in our table. And what we get is for the copper, it's 0.34. So for the copper, 0.34 volts, and for hydrogen is going to be 0 because it is the standard. So 0, the electrochemical, the electrode potential is 0.00 volts. So if you do cathode minus anode, so the electro potential of the cell is going to be equal to the cathode 0.00 volts minus 0.34 volts. So we get a negative 0.34, 4 volts. So that is the electrochemical potential of the cell. So now what we can do is, now that we have the electrochemical potential of the cell, we can use the standard electrochemical potential of the cell. We can plug it into this equation here and solve for K. So here we plug this into K. So this is going to be negative 0.34. We're using this equation right here. So the standard electrochemical potential of the cell that we got here, negative 0.34 volts, is equal to this, so it's going to be 0.0592 Let me make sure I got that right. Yeah, so this is going to be volts. The number of moles of electrons that are being transferred is 2 moles of electrons. So that's going to be 2 moles of electrons, and that's going to be the log of K. So all you need to do now is solve for K. And so what you can do there is we could solve this. So if we do that, that's going to be, if I use my calculator. Alright, so what we end up getting is that the log of K, so then you solve this, you get the log of K is equal to negative 11,486. Negative 11,486. We keep an extra digit just in case for rounding errors. And now when you do the log, to solve the log, you raise everything to the power of 10 because log base 10 is log is log base 10. So if you raise this, it'll be 10 to the log of K is equal to 10 to negative 11,486. Raising a log to as a base as a power of base 10. That's basically the same thing as taking the square root of a square. The square root of a square cancel each other out, and you're left with whatever's left over. So here, the log and the base 10 cancel each other out, and you get K. So then that tells you that K, the constant, is equal to 10 to the negative 11,486. And if you calculate that out, you get 3.3 times 10 to the negative 12. So that would be the K value for this redox reaction. All right, well, what about number 2? So number 2, same thing. We got to do the same thing. We're going to break this up into its 2 half reactions. So here we have iron. So we have 2 iron solid, and that's going to iron 3 plus. So we're going to lose electrons. So here we're going to 2 iron 3 plus. That means that we lost a total of 6 electrons. So here we have 6 hydrogen plus aqueous. We're going to gain 6 electrons to get the 3 hydrogen, so that's plus 6 electrons, and that's going to give us 3 H2 gas. And so now what we're going to do is we're going to now look up the electrode potentials for these 2 half reactions. So iron, this is losing electrons, so this is oxidation. And again, oxidation happens at the anode, and we're gaining electrons here, so that's reduction. So reduction, and that's happening at the cathode. And so now we need to look up the electrode potentials for these. Okay, so for iron 3 plus, let's see. That would be 0.036, so a negative. So the electrode potential for this is going to be a negative 0.036 volts. And again, for hydrogen, H plus, going to H2, that's going to be 0. So the electrode potential for this is going to be 0.00 volts because, again, that's the standard. Okay, so now if we subtract these two, so the electrochemical potential, standard electrochemical potential is equal to cathode minus anode. So 0.00 volts minus negative 0.036 volts, and that's going to be equal to positive 0.036 volts. Okay, so now that we have that, we can now take this and plug it into this equation here. And so here, so our standard electrochemical potential of the cell is plus 0.036 volts is equal to 0.0592 volts over the number of electrons, or number of moles of electrons. Here we're doing 6, so we got 6 moles of electrons multiplied by the log of K. And again, we solve K the same way as we did before. So we're going to use our calculator. Okay, so that's going to be 3.648. So that's going to be plus 3.648. Let me double check. 3.648 is going to be equal to the log of K. And then if we do the same thing here, what we're going to end up with is K is equal to 10 to the positive 3.648, which is going to be equal to, okay, and that's going to be 4.45. So 4.45 times 10 to the third, I believe. And so that's going to be the K value, the constant, the equilibrium constant for this redox reaction. So I hope you found this to be helpful. These are a couple good examples of how you can calculate the equilibrium constant from the electrode potentials of a redox reaction. If you like this video, if you like my videos, please like, share, subscribe, hit the notification bell, and leave a comment in the comment section. Thanks for joining me, and I'll see you next time.